So we're going to start our first real section in Unit 1. Unit 1 deals more in atoms and elements, and then gets into how things bond. So we get a more in-depth method or idea or concept of how things are bonding. So instead of just knowing ionic and covalent and knowing metal, non-metal, as well as non-metal, non-metal, we actually look at how things are sharing. We look at the electron diagrams. We go into way more detail than we have in the past. Okay? So the first kind of section is just kind of looking at some history of the atomic theory. Okay? Now, this is basically a really old PowerPoint. So when PowerPoint really first came out, that was like about 15 years ago, when I was just starting into teaching. So realize that some of this stuff, there'll be lots of sound effects, lots of those side flicker things and all that other stuff. So just kind of ignore all my extra little PowerPoint crap. Okay? I'm sorry. But the history of the atom hasn't really changed. Okay? It's a story of many other different scientific theories, just like before, where some guy has this idea, and then, oh, but have you thought about this? And then they do some tests, and they change their idea based on some scientific evidence. So the first is ancient Greeks. Aristotle, he believed in 4 elements. Everything on this earth was made up of the 4 elements: earth, water, air, and fire. Okay? So how did you get any kind of substance? So like a substance like coffee. Well, it's a mixture of water and earth, probably. Okay? Or something like that. Okay? Jalapenos probably had some fire to it, right? I'm just saying it's a mixture of those 4 elements. So he believed that everything was made out of those 4 elements. Now, there was this guy back in the day, he was still in Greece, called Democritus. He said, I think matter is made up of these tiny little particles that are always in motion and had some of these characteristics. They're invisible, they're solid, they're indivisible, they're eternal, and they're surrounded by empty space. Okay? Kind of ahead of the time back then, right? Kind of amazing, because that's kind of what we kind of think of as matter right now. There are a few little misconceptions, but overall, this was a good idea of an atom, okay? Little tiny particles that were in motion and had these characteristics, okay? Now, the other thing is, I printed off you guys a copy of this, but if you feel need to add things in or to highlight certain things or to put stars next to things that I'm telling you is important, I would do that, okay? Now, if you knew anything about some past history, Archimedes and Democritus were at the same time. Okay, and I think I've talked about these 2 guys before. Basically, Archimedes, he disagreed with Democritus. Okay, what was Archimedes? Fire, wind, fire. No, I said fire twice. Air, and earth, and water. Now I said it twice again. Oh, so he believed in 4 elements. Okay, and this other guy said, I think everything's made out of little particles that are in motion, that blah, 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 blah. Now, guess who the people believed? Okay, Archimedes for a couple reasons. Okay, neither one of them had real proof, right? They couldn't definitively show the people, okay, this is what it's made out of. But Archimedes was very highly respected, okay? So basically, Archimedes, just put it here. He was highly respected, and everyone kind of believed what he said. So he was one that was like a man of the people, right? Or was highly social, okay? And he was probably up in ranks, like, you know, when you talk about different ranks of society, he was probably a higher ranked person in society. Okay? So, when Archimedes laughed at this guy's idea, everyone else followed along with him and continued to believe in the ideas of fire, earth, air, and water. Did I get it right this time? Okay? So, even though we have this idea of tiny little particles, perpetual motion, we get there. Sorry. So, then we come upon a time where science wasn't very important. Do you guys know when science wasn't very important and war and killing happened lots? The Middle Ages, the Dark Ages, stuff like that. All right? So, the early information was lost, wasn't cared about. Basically, during the Middle Ages, people began reinvestigating nature and structures of matter. So, what do they want to go through? Transmutation. You guys know what transmutation is? Changing certain elements into gold, right? Or into noble metals. So they really wanted to change regular metals into gold. Why? So they get rich. It's a currency, right? Why not? It would be very important for that. Okay? So they try and transfer or change this plain metals into things. So you can really think the alchemists, they did some observations, then they did experiments and measurements and classification. They kind of started with this scientific method here, right? To observe, to experiment, okay? Let's measure, figure out what we got, okay? Oh, maybe we need to try again. So we jump from before Christ to the dark Middle Ages, and now we're in 1600s. Okay? So this guy's named Boyle. He came up with the idea that matter was made out of simple substances called elements, and elements were substances that could not be further decomposed or broken down. He had no proof. He had qualitative experiments. Qualitative is just deciding what's in it, no quantity, not how much of something. Okay? Then, another 100 years go by. We get Lavoisier. He developed quantitative experiments needed to prove Boyle's theory. So basically, he took mercury and oxygen and combined it together and made mercury oxide. So he measured the amount of mercury he had, 200 grams, measured the amount of oxygen, and then he bonded them together and got the same amount of mercury oxide. Okay? So basically, he heated mercury and air, and the silver mercury turned into a red product, which was heavier. So they combined them. So he had an idea to prove that this element plus this element bonded together to make a new molecule. So basically, he got some quantity to prove about elements. Okay? To explain the increase, he tried to reverse the process. So take the red substance and break it into its two parts, into the silvery metal and to the gas. So when he heated the red product, he collected the gas. He found that the amount of oxygen produced was equal to the increase in the mass of his first reaction. So the amount that he actually collected was equal to the amount that this red substance increased. Okay. This also came to demonstrate the law of conservation of mass. Matter is not created or destroyed during a chemical reaction. It's just moved around. And he said that certain substances are elements, a substance that cannot be broken down into simpler substance by chemical means. So you can't break them down any further. So in his time, he found some simple substances which he considered elements. So he found light, caloric, which is heat, oxygen, which is just basically air for him, azotite, hydrogen, and then all of these different metals he found, okay, and classified them as elements. So if you take a look, most of these are elements that we find on the periodic table of elements. So he actually found some basic substances that you would consider elements. Okay? Now, some of these other substances, okay, sulfur, phosphorus, chalk, some of these aren't simple elements, okay? So chalk is now calcium carbonate that we know, which is calcium and carbon and oxygen bonded all together, but he couldn't figure out a way to break it down any further, so he thought of it as an element, right? But in time, new experiments, new technology, things change, okay? You guys have probably heard of Dalton. Dalton is a key, can I stress this again? Key contributor to the history of atomic model, okay? He actually did the first major contribution for the first atomic theory based on experimental evidence, okay? So there's actual evidence that he can back up some of this information with, okay? He reintroduced the idea of an atom based on scientific experiments. So whose idea was this atom anyway? Democritus or Aristotle's idea? Democritus. So Democritus, way back then before Christ, came up with this idea of these small molecules that are in perpetual motion together, okay? Or small particles, I guess I should say. So Dalton first said small particles are called atoms. They cannot be subdivided. They cannot be created or destroyed. The properties of one atom are identical. Properties of atoms of different elements differ. Okay, so if you have a carbon atom and another carbon atom, they're going to look exactly the same, they're going to act exactly the same. But if you have a carbon atom and an oxygen atom, they're going to look differently and they're going to act differently, is basically what he's saying. And then atoms can combine in simple ways to form compounds. In definition, whole number ratios. So H2O, CO2, C6H12O6. Okay? So he had a lot of these different ideas. Do you agree with all of these? Probably most of them you could say that are probably something that you know or believe. Okay? So then we have Thomson. Okay? He's important because he actually discovered the electron. And what do you guys know about the electron? It's got a negative charge. Where is it? It's a part of the atom. The atom isn't the smallest thing on the world. The atom is made out of different things. Electrons, protons, and neutrons. Back in the day, you guys, they thought an atom was a solid thing, and that was it. That was the smallest thing but now we know, oh wait, there are these things called electrons. At this time, 1897, they do not know about the nucleus, they do not know about neutrons, they do not know about protons. The only thing they know is that there's this thing that's the smallest thing on the earth, a particle called the atom. This guy goes, whoa, 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 whoa. I found electrons. Okay? So, he proposed this first model. Some of them call it his plum pudding model. Some of them call it chocolate cookie dough model. No, I always know it as the plum pudding model. Some of them call him raisin pudding model. It basically is that the atom is a pudding, and the electrons are all inside of it, all floating around, and that's represented by the raisins or the plums inside of the pudding. So at this point in time, they didn't realize the electrons are on the outside. They didn't realize about the nucleus. They only decided that, hey, we discovered these electrons, and this is what an atom looks like now. Okay? A sphere of positive substance mixed with negative electrons. Raisin pudding, plum pudding, they call it a few different things. Okay? So we got electrons. Now, in 1911, so just over 100 years ago, right? And we noticed this about science lots, you guys. The fact that back in the day with a very little technology, very little concepts, or they never really focused on science, right? They focused on taking over the world and social and fighting and wars and different things like that were more important to them back then, right? Or just actually figuring out how to live in some harsh conditions on the world. But now, as we get more technology advanced, we get more ideas and concepts popping up in science. So he did this oil drop experiment. So he took a spritzer, basically, and sprayed tiny particles of oil droplets. Okay? There's a positive charge plate here and a negative charge plate here. And he looked in here, and as the oil droplets fell, he noticed something. Okay? Oh, didn't explain what he noticed. Basically, things started floating, right? So the oil droplets were charged. Hi. Oil droplets were charged, and then he actually was able to come up with some electron stuff. Okay? And there's Rutherford. Okay, 1912. His students were doing experiments with radiation, and he shot alpha particles at gold foil, really, really thin gold foil. He thought that the spaces in the atoms were mainly empty, but some particles were reflected, okay? And so he was the one that noticed that there was something there, okay? That the atoms were not invisible, okay? That there was some sort of piece of atom there. He discovered the nucleus. Important guy, discovered the nucleus. Okay? The fact that there was something in the center of the atom that actually made holes in this gold foil. Okay? So by 1912, we had discovered the nucleus. So let's go back, just so we know. In 1897, we discovered an electron. In 1912, we discovered the nucleus. So that's over, 15 years? Okay? So lots of things are coming fast about the atom right now. Okay? The positive charge, or the majority of the atom's mass, was concentrated in the small part. This is what we noticed. So Plum's pudding model is kind of gone by the wayside, okay? It's not a positive sphere with electrons floating inside of it. Now we have this planetary model, okay? So this is just his experiment where he shot it and things got reflected and he made those decisions, okay? Now, sorry, the planetary model, have you guys watched Simpsons? Is that show still on? They have that atom where the electrons are floating around in orbits. That's Rutherford's method. Okay, that's the planetary model. So then Bohr in 1914. Orbits can't be anywhere, they're quantified. Okay? Quantified like specific numbers. And I remember you guys, you know when I said there's N1 shell, N2 shell, N3 shell? Back in Science 10 when we talked about the different rows being shells, okay? This is getting into Bohr's model. Generally, the distance from the nucleus is the greater the energy of the electron. Because the center is a positive and the electrons are negative, so as you move further and further away, you have to have a stronger pull to stay right next to that nucleus, right? So the energy of the electrons further away are the greater the energy of the electrons. And orbits became known as energy levels, and we will actually talk about energy levels throughout this semester here. Every atom in its normal state, just like every student in its normal state, wants to do the least amount of energy or the least amount of work, right? I don't know about that. Maybe not all students, but lots of times you want to do the little amount of energy or use the least amount of energy to get something done. That's just like electrons. So if they want to, they're going to be in the lowest energy levels. This is classical physics, even, just so you know. This is the Bohr model. So now instead of each electron being on its own path, we have electrons in energy levels. And we get this because we count the first energy level has 2 electrons because we count over 1, 2. The second energy level has 8. Okay, 1, 2, 3, 4, 5, 6, 7, 8. Now the third energy level, he says, has 18 or something like that in here. But we'll get into more Bohr model stuff as we go into more detail here, but just not on this day. So that's all classical stuff. Okay? We have to have some modern stuff in here as well, because that's where we actually think it is now. But remember that all that classical stuff helped us build up our idea. And right now we know about electrons, and we know about the nucleus. So atoms have many parts, and they're a complex organization. These are the list of Dalton's ideas that are still useful. So if you want to know Dalton's ideas that we still use, it's right here. Elements are made out of atoms. Compounds do form by joining atoms in fixed whole number ratios. Properties of atoms of one element are identical, and properties of atoms of different elements differ. But there are some differences that we take away from Dalton's original ideas. Atoms can be subdivided, and we did find out about protons, neutrons, and electrons. Okay? Neutrons, I believe, was discovered in 1932 by Chadwick. Okay? Protons were kind of always there because we always had a positive and a negative effect, but now we know when we discovered neutrons that the atom, the nucleus of the atom, was made up of protons and neutrons. Atoms can be changed from one element to another, but only by nuclear reactions. Okay? So that's like radioactive decay is when we change from one. There's no transmutation, no turning lead to gold. We still can't do that. Okay? But we can go through radioactive decay in which one element turns into another element. And atoms of the same element are not all exactly alike. They're alike in the characteristics or their properties, but sometimes they can have isotopes or ions, right? Which means they have different number of electrons or they have different number of neutrons. Okay? So just because it's a carbon atom, it doesn't mean that it has the exact same number of electrons and neutrons. It means it has the exact protons, and it has the same kind of chemical properties or physical properties. So here we go. We've got protons discovered in 1886, electrons discovered in 1897, and we have neutrons in 1932. Just kind of gives you an idea of what's going on. Moving on into quantum physics, this is where we think of the atom right now, and we'll have to go into more detail of this atom in a little bit of time. But this is Schrödinger. I always say his name wrong, because that O with the double dots over top, he's if I remember right, German. Okay? So he came up with some of these ideas. Obviously, he works amongst different scientists and they work together and collaborate, but he was the main contributor. He came up with this idea of electron probability. Have you guys heard anything about his cat before? Like you read jokes about his cat and stuff like that? That's a joke on his idea of atomic theory, okay? So basically, elements, they have this probability of the electron being in this certain orbital or this orbital. They all have different shapes, and they're called the charge cloud models. They don't have paths, they just randomly fly around the atom in this orbit, or charge cloud, okay? Now, these are his different charge clouds. There's spheres, and there's P's, which I think look like propellers, so it reminds me that they're P orbitals. They look like propellers. And then there's D's, and it carries on. So the S's are the sphere shaped cloud, and they're actually the first two columns of your periodic table. So any electrons that are in the first two columns of your periodic table are in sphere-shaped orbitals. Your P-shaped orbitals, your X, Y, and Z P's, are column 13 to column 18 electrons. They land up in here. Your D-type orbitals are like your transition metals, and then there's F-type orbitals, which are the ones that are your lanthanoid and your actinoid ones. Okay? They get even more complex. The shapes that we really need to know about are your S's and P's, but we will also fill D-type orbitals, but I won't ask you, is this the dx squared orbital? Okay? So, here's your Schrodinger cat. Basically, his idea is that the electrons have a 99% probability of being in this charge cloud part. Okay? So, play on Alice in Wonderland and play on Schrodinger's cat. So, review. Over the last 200 years, but basically in the past 100 years, 150, there's been lots and lots of modification on the concept of matter. But after 1932, 1950, right around in there, we haven't really made much changes to the thought of what atomic particles or what atoms really look like. We do go into more detail and look at more things, but the general idea has not changed. Okay? The big thing, and what you'll see more and more of in your life, is technology and the idea of actually being able to visually see something or to take data to quantify it, okay, to actually realize what's going on will affect how we think and see things in our world, okay? We get more and more technology and we see more technology that will actually have us quantify things, right? To have data and numbers to back it up, okay? Which are very helpful. And atoms, they're not those solid spheres that they used to think of, but they have a combination of smaller parts which make them very unique in structure and function. And we will look into this structure and function in more detail as we carry on in this first unit. Okay? We're going to end here for today. So those of you that need to get your student-directed study, your science fair idea or concept written down, this is a perfect time for you.